You're about to meet a star so extreme it shouldn't exist. A city-sized object with more mass than the sun, a magnetic field that can tear atoms apart, and explosions that can rattle Earth from halfway across the galaxy. This isn't a black hole, it's something stranger, a magnetar, the most powerful magnet in the universe. But before we continue, please subscribe to the channel to give your support. Let's continue. Here are the basic facts. A typical magnetar is about 20 kilometers across, roughly 12 miles. That is small enough that you could drive across its diameter in under an hour if roads and normal gravity existed there. Inside that 20-kilometer sphere, you have more mass than the sun. You take the sun's entire mass and crush it into a ball the size of a city, and the result is a neutron star. A magnetar is a neutron star with a magnetic field so strong that it becomes the main character. That field can reach around 10 to the power of 11 Tesla, which corresponds to roughly 10 to the power 15 Gauss. You can skip the exact numbers. The takeaway is that this is the strongest magnetic field we know of in the universe. That compression turns matter into something fundamentally different from anything around you. Take an ordinary tablespoon from your kitchen and think about scooping one spoonful from a magnetar surface. That one spoonful would weigh more than 100 million tons. As a rough comparison, that is like cramming about 100 of the world's largest aircraft carriers into the space of that spoon. Gravity is so intense that electrons are forced into protons to make neutrons, and those neutrons are packed almost with no empty space between them. You are no longer dealing with rock, water, or metal. You are dealing with nuclear density matter, basically one giant atomic nucleus held together by extreme pressure and by quantum physics. Surface gravity follows the same pattern. Everything is pushed to an extreme. If you could somehow stand on a magnetar, each step would not feel like a few G's like you get in a fighter jet or on a roller coaster. It would feel like billions of G's. Your body, your gear, even the atoms in your bones would be crushed into the surface instantly. Light escaping from that gravity well loses a noticeable amount of energy just climbing away, something we call gravitational redshift. Space and time themselves are strongly curved only a few kilometers above the surface, all inside an object only about 20 kilometers wide. It is a compact gravity well, not a diffuse ball of gas. So density and gravity are already way beyond normal stars, but the real headline is the magnetic field, because that is what makes a magnetar break everyday rules. Compare it with magnetic field you actually know. Earth's field at the surface is about half a Gauss. A fridge magnet is a few hundred Gauss. The strongest continuous fields we can make in a laboratory are around 10 Tesla, about 100,000 Gauss. A magnetar can sit up at 10 to the power of 14 to 10 to the power of 15 Gauss. That is on the order of 1,000,000 billion times stronger than Earth's field. At that strength, the field is not just something that turns compasses. It dictates how charged particles move. It distorts atoms and even changes how light propagates near the star. Now, put that into a scenario that directly involves you. Place a magnetar not right next to Earth, but part way to the moon, at a distance of about 60,000 kilometers, around 37,000 miles. You do not need an impact. You do not need an explosion. You just let the magnetic field reach us. At that distance, it would be strong enough to erase every magnetic strip on every credit card, corrupt a lot of data storage, and heavily disturb satellites and power systems. But the more disturbing effect is deeper. The magnetic field would start to tug on the electrons in your atoms. Chemistry relies on electrons sitting in specific patterns around nuclei, forming bonds and structures. A magnetar's field pulls on those electrons so strongly that those patterns get stretched and squeezed out of shape. Closer in, the field becomes strong enough to rip electrons away entirely and tear molecules apart. In that lethal zone around the star, matter is not acting as solid, liquid, or gas. It is just charged particles forced to follow magnetic field lines. With something this extreme, it's natural to hope that magnetars are very rare, maybe one or two oddballs per galaxy. Observations and models say that's too optimistic. With current X-ray and gamma-ray telescopes, astronomers have identified only a few dozen magnetars in and around the Milky Way. They show up as compact sources producing steady high-energy emission, sometimes with short, intense bursts. That sounds like a small number, but those are just the active ones shouting in X-rays. When researchers model the life cycles of massive stars over billions of years and ask how often a core collapse should leave behind a magnetar instead of a more ordinary neutron star or a black hole, they get a much larger expected population. The calculations suggest there could be tens of millions of old magnetars in our galaxy, whose magnetic fields have weakened over time and no longer make them stand out in X-rays. So your galaxy is probably full of quiet magnetar corpses, dark remnants that no longer flare but still exist as compact, invisible objects, still crushingly heavy, still with strong gravity, just no longer broadcasting with powerful bursts. We only notice the minority that are young enough or magnetically active enough that their fields are still decaying rapidly and heating their surfaces. That brings you to the key question about energy. If these objects aren't powered by the same engine as the sun, what keeps them shining at all? In a normal star, the core fuses light elements like hydrogen into heavier ones, and the energy from that fusion moves outward and escapes as light and heat. By the time you have a magnetar, that phase is over. The core has collapsed. The matter is already in an ultra-dense neutron state, and ordinary fusion can no longer power the star. The main energy source is the magnetic field itself. If a star this small can do all of that, what kind of stellar death could create it, and how violent does that birth have to be? How do you take a normal, massive star and turn it into the most dangerous magnet in the galaxy? The answer starts very simply. You pick a star that's too big for its own long-term survival. Then you let physics run all the way to the end. You begin with a star around 10 to 25 times the mass of the Sun. In metric, that is roughly 2 to 5 times 10 to the power of 31 kilograms. In simpler terms, you're talking about a star that weighs a few million times more than Earth, all in one place, burning nuclear fuel at a furious rate. On the outside, it looks beautiful, bright, stable, but inside it is constantly balancing two huge forces, the inward pull of gravity and the outward push from nuclear fusion in the core. As long as there is fuel, mostly hydrogen and then heavier elements, that balance holds. The core burns hot and the star supports itself. So what actually breaks that balance? What flips this from just a big star into the setup for a magnetar? Eventually, the core runs out of useful fuel. It builds up heavy elements like iron that do not release energy when you fuse them. When that happens, the fusion power drops, the outward pressure collapses, and gravity, which has been trying to crush the star the whole time, finally wins. The core starts to fall in on itself, and it does not do that gently. It collapses. During this core collapse, the change in size is brutal. The central region, originally on the scale of something like Earth's size, a few thousand kilometers across, shrinks down to about 20 kilometers, about 12 miles. That shrinkage happens in a fraction of a second. When the core hits nuclear density, the matter stiffens, the collapse slams to a stop, and a shock wave forms. That shock, plus energy from neutrinos pouring out of the core, blasts the outer layers into space as a core collapse supernova. From far away, you see an explosion that outshines an entire galaxy for a short time. At the center, left behind, there is now a compact object, a neutron star. If that story stopped there, you would just have an ordinary neutron star, still extreme, but not yet a magnetar. The next piece comes from rotation. Before collapse, the star is spinning, maybe once every few days. When the core shrinks from thousands of kilometers to 20 kilometers, its moment of inertia drops drastically. Angular momentum is conserved, so the spin rate shoots up. It's the same basic idea as a skater pulling in their arms, but here the arms shrink by a factor of hundreds, so the spin can jump to hundreds of rotations per second. You now have a newborn neutron star, only 20 kilometers across, spinning so fast that a point on its equator is moving at a significant fraction of the speed of light. So how does that insane spin turn into an insane magnetic field? What takes a normal neutron star and pushes it into the magnetar category? Inside that newborn neutron star, the matter is extremely hot and fluid, and it's threaded by an existing magnetic field from the parent star. Rapid rotation plus turbulent motion in a conducting fluid is exactly the recipe that powers dynamos in planets and stars. In this environment, the dynamo effect can run at extreme settings. It takes an already strong magnetic field, maybe around 10 to the power of 8 Tesla, and amplifies it up to around 10 to the power of 11 Tesla. In older units, that's up to about 10 to the power of 15 Gauss. Compared to Earth's field, you're cranking it up by roughly 1,000 trillion. The key point is that this is not just a random story someone made up to sound dramatic. In the 1990s, theorists worked out these magnetar dynamos on paper and in simulations. They predicted that such objects would show up as neutron stars with relatively slow spin periods, strong magnetic fields, and persistent X-ray emission, plus occasional bursts. Later, when satellites found objects called soft gamma repeaters and anomalous X-ray pulsars, their behavior matched those predictions, including the spin periods and magnetic field strengths. That's why the community now treats this dynamo channel as the main way magnetars are born, a rapidly spinning, hot neutron star amplifying its own field during the first seconds to minutes of its life. If this process is so powerful, does that mean every massive star collapse leaves behind a magnetar? The answer is no, and that's important. Not every core collapse supernova has the right conditions. You need a star in the right mass range, you need the core to retain enough angular momentum, you probably need some specific internal structure. Based on supernova rates and the number of neutron stars we see, estimates suggest that maybe 1 out of 10 core collapse supernovae produces a magnetar. The rest produce ordinary neutron stars, or black holes. 1 in 10 may sound like a small fraction, but remember, the Milky Way has been forming stars for more than 10 billion years. Over that time, even a small percentage adds up. So our galaxy has likely built a huge population of magnetars, most of which have already calmed down and gone quiet. If only a minority become magnetars, is there any way to spot which explosions had one at the center, especially when the compact object itself is too small to see directly? This is where you look at the brightest, weirdest supernovae we know. Some supernovae are not just a bit brighter than normal, they're 10 to 100 times brighter. Their light curves, the way their brightness rises and fades over time, don't match what you would expect from a standard explosion powered only by radioactive decay of heavy elements. Instead, they look like there's an extra engine pumping energy into the expanding debris. When you plug a newborn magnetar into the models, things start to line up. A rapidly spinning magnetar with a magnetic field of around 10 to the power of 15 Gauss has a huge reservoir of rotational energy. As it spins down, it can dump energy into the surrounding material at rates up to something like 10 to the power of 45 watts for days or weeks. That injection keeps the debris hot and bright for longer than usual, and it shapes the light curve in a way that matches those superluminous events. In other words, in some of the most extreme supernovae, the central magnetar acts like a hidden engine, invisible directly, but obvious from the way it forces that patch of the galaxy to blaze far beyond normal. So now you have the basic picture. A massive star burns through its life, its core collapses, a rapidly spinning neutron star forms, dynamo action cranks its magnetic field up to absurd levels, and in a fraction of a second, you've built a magnetar. Only the wildest, most energetic explosions make them, but over the age of the Milky Way, even that small fraction has filled the galaxy with magnetic time bombs. Some still active, many already faded. The birth is violent, but the real shock comes later when you ask what that kind of magnetic field actually does to space, to atoms, and even to the vacuum itself. How strong does a magnetic field have to be before it stops behaving like the magnets you know and starts rewriting matter around it? Magnetars sit way past that point. Their magnetism isn't a small detail. It's the main thing that controls what happens near them. Start with numbers you already have a feel for. Earth's magnetic field at the surface is about half a Gauss. A basic fridge magnet is maybe 100 Gauss. The strongest continuous magnetic fields humans can create in a lab using huge machines and a lot of power get up towards about 100,000 Gauss, which is around 10 Tesla in metric. Those are already serious engineering challenges. A magnetar doesn't sit in that range. Its field can reach around 10 to the power of 14 to 10 to the power of 15 Gauss. That's roughly a million billion times stronger than Earth's field, and in Tesla, up to about 10 to the power of 11 Tesla. At that point, you're not just scaling up something familiar. You're in a regime where our usual experience gives you no help at all. So the field strength is huge, but what does that actually mean in terms of energy? Why does it matter that the field is that strong? Magnetic fields carry energy. In a magnetar, the energy stored in the field inside and around the star is enormous. If you take the energy in a small region of the field and use Einstein's relation between mass and energy, you can assign it an equivalent mass. When you do that, you find that the effective density of the magnetic energy can be something like 10,000 times the density of lead. In other words, even if you ignore the neutron star itself, the magnetic field alone contributes a noticeable amount to the total mass and gravity in that region. You're not just dealing with invisible lines drawn in space. You're dealing with a physical field that has weight in a very literal relativistic sense. So the field is that energetic. What happens to the atoms that are unlucky enough to sit inside it? How does it treat the basic building blocks of matter? Under normal conditions, atomic orbitals are roughly spherical clouds where electrons move around the nucleus. The shapes get more complex for heavy atoms, but they're still three-dimensional blobs that you can describe with standard quantum mechanics. In a magnetic field of about 100,000 Tesla or more, those orbitals start to deform. The field forces the electrons to spiral along its direction, and the atom becomes stretched out along the magnetic field lines and squeezed in the other directions. Crank the field up to around 10 billion Tesla, which is the magnetar regime, and even a simple hydrogen atom becomes about 200 times narrower than it is under ordinary conditions. Once you are there, chemistry as you know it stops working normally. Chemical bonds, electron shells, and typical atomic structures are built assuming that electromagnetic forces dominate, and that magnetic fields are weak enough to be almost a side effect. Near a magnetar, the magnetic field is so strong that it dictates where electrons are allowed to be. Bonds that would form on Earth may not exist at all. New, highly directional bonds can appear along the field lines. Matter is forced into elongated, rod-like structures. Physicists sometimes call this spaghetti-like behavior, not to be poetic, but because the atoms really are pulled into long, thin shapes by the field. If atoms are being stretched and crushed like that, what happens if you, as a collection of atoms and molecules, get close to one of these objects? There's a region around a magnetar that you can think of as a kill radius set mainly by magnetism. Within about 1,000 kilometers of the star, roughly 620 miles, the field strength and its gradients are so high that they start to seriously distort the electrons in your atoms and tear apart molecules. You do not get torn apart by gravity as you might near a black hole, where tidal forces stretch you in one direction and compress you in another. Here, the damage comes from magnetic forces acting differently on different parts of your body and on different charges inside each atom. Electrons and nuclei feel different pushes, bonds break, and normal matter can no longer hold together the way it does in everyday life. From an astronomical point of view, 1,000 kilometers is a very small distance. The star itself is about 20 kilometers across, so the lethal magnetic zone is only a shell a few tens of radii away from the surface. But inside that volume, the rules that describe solids, liquids, gases, and even plasmas in normal environments simply do not apply in their usual form. The field is too strong. The gradients are too steep, and matter is forced into states that we cannot reproduce in Earth-based labs over macroscopic volumes. If the large-scale field is already that extreme, you might expect it to at least be smooth and simple, like a giant bar magnet in space. The reality is worse. Observations show that some magnetars have relatively modest dipole fields when you estimate them from their spin down, yet they still produce strong bursts and show signs of intense local magnetism. That tells you that the field is not just a simple global structure, it is twisted and knotted on smaller scales. In some regions, only a few hundred meters across, the local field strength can hit around 10 to the power of 15 Gauss, even if the average field over the whole star is lower. One example is an object called SGR 0418 plus 5729. When astronomers first measured it, its large-scale dipole field seemed weaker than you would expect for a classic magnetar, but its behavior, especially its bursts, said otherwise. The simplest explanation is that the external dipole field is only part of the story. Under the surface and near it, there are strong, tangled components, like tightly wound loops and twists in the magnetic structure that store extra energy. Those local hotspots can snap and rearrange, powering bursts and flares even when the overall field looks modest on paper. This means a magnetar is not a clean, predictable magnet scaled up to cosmic size. It's more like a star-sized knot of magnetic tension, with strong fields on large scales and even stronger pockets on smaller scales, all slowly shifting and decaying. The more closely you look at the magnetism, the more complicated and dangerous it becomes. If the field alone can bend atoms, crush chemistry, and inject real mass into space through its energy, what happens when that field starts to move, twist, and break the solid crust of the star itself? How does something this dense and compact ever break? How can a star made of nuclear matter have quakes at all? The answer is that a magnetar is not just a uniform ball of neutrons. It has structure, and that structure is under constant stress from the magnetic field. On the outside, there's a rigid crust, roughly a kilometer thick, about 0.6 miles. It's made of a crystal lattice of nuclei, extremely strong compared to anything on Earth, but still a solid layer sitting on top of something very different underneath. Beneath that crust, the interior is not a regular liquid. It's a superfluid and a superconductor. The neutrons flow with almost no friction, and the protons form a superconducting fluid that carries currents with zero resistance. The magnetic field threads through this whole system, from the core up through the crust and out into space. The field lines are anchored in the crust, but they also want to move, twist, and rearrange as the star cools and the internal currents evolve. That creates a problem. The magnetic field is trying to drag the field around. The field is tied into the crust, and the crust resists for as long as it can. Over time, that mismatch builds up stress. You can think of it as a slow, relentless shearing force, with the magnetic field trying to shift its foot points and the solid crust saying no for as long as it can. The stresses involved are far beyond anything any rock on Earth could handle. Steel beams, Earth's tectonic plates, none of those come close. The magnetar crust holds until the accumulated stress exceeds its breaking limit. So what actually happens when the crust can no longer take it? What does failure look like for a kilometer-thick shell wrapped around a 20-kilometer star? At some point, in some region, the stress exceeds the yield strength and the crust fractures. Astronomers call this a starquake. It's not a gentle bend, it's brittle failure in ultra-dense material. A crack opens, it can propagate over a huge area, and the solid lattice suddenly shifts to a new configuration. In a few milliseconds, a large patch of crust can move by centimeters or more, releasing a massive amount of elastic energy. The energy involved is extreme. A single starquake can release more than 10 to the power of 25 joules almost instantly. To give that a rough sense of scale, that's more energy than the entire United States uses in years, dumped in a fraction of a second. The most powerful earthquakes on Earth are tiny by comparison. On a magnetar, this is just one crack event in the outer kilometer. The interior doesn't care much. The overall star survives, but the crust has just gone through a catastrophic failure. Now, you might ask, if the crust cracks, why does that matter for space around the magnetar? Why would a fracture inside change what satellites see tens of thousands of light years away? The key is that the magnetic field lines that fill the magnetosphere are rooted in the crust. When the crust shifts, it drags those footpoints with it. That sudden motion yanks on the field lines, twists them, and forces the magnetosphere to reconfigure. You're not just breaking rock, you're jerking on a star-sized magnetic structure that extends far into space. When that happens, the magnetosphere reacts violently. Twisted field lines can reconnect, snapping into new shapes, and that process accelerates charged particles to huge energies. Electrons and positrons are flung along the field lines. They slam into the star's surface. They radiate X-rays and gamma rays as they spiral in. From far away, what you see is a sharp spike in high-energy emission, a burst that might last milliseconds to seconds. Those are the soft gamma repeater bursts and magnetar flares that our satellites detect, short, intense flashes that line up with the idea of a crustal fracture kicking the magnetosphere. You could still wonder if this is just a nice theoretical story, or whether we have actual data that points to the crust vibrating. This is where some very specific magnetar events come in. Objects like SGR 1806-20 and SGR 1900+14 have produced giant flares where, after the initial spike, the X-ray light curve shows quasi-periodic oscillations, repeating wiggles at frequencies of tens to hundreds of hertz. That means the brightness is rising and falling many times per second in a regular pattern. Those frequencies are not random. They line up with the expected vibration modes of a solid crust on a neutron star, and with coupled modes, where the crust and magnetic field oscillate together. It's as if the quake hits, the crust snaps into a new shape, and then the whole star rings in a set of preferred tones. As it rings, the magnetic field and the emission pattern wobble, so the observed X-rays get imprinted with those frequencies. You're literally watching a 20-kilometer star shake, not guessed indirectly, but read out in the timing of the high-energy light. This directly challenges the older picture of neutron stars that dominated for decades. In that older view, a neutron star formed, cooled down, spun, and very slowly lost energy, acting mostly as a stable, rigid object with maybe some radio pulses or steady X-ray emission. Magnetars show that this is incomplete. Their crusts are not just passive shells, they're dynamic, stressed, and capable of catastrophic failure. Their interiors are not just quiet superfluids, they're supplying the currents and fields that keep loading the crust with stress. Deeper inside, near and below the crust base, the matter may form what theorists call nuclear pasta, weird shapes like rods and slabs that minimize energy at extreme densities. Those structures change how the magnetic field and heat move through the star. Over thousands of years, not millions, magnetars evolve as their fields drift, their crusts yield, and their internal structure shifts. You have to treat them as plastic, changing objects, not frozen relics. So now the situation looks more unstable than before. You have a tangled, ultra-strong magnetic field, anchored in a crust that can crack, sitting on top of a superfluid interior that keeps pushing. Individual starquakes already produce dangerous bursts, but these are still small compared to the most violent events magnetars can produce. The real escalation comes when the entire magnetosphere is rearranged in a single enormous outburst that can affect Earth from across the galaxy. How dangerous can a star really be if it is sitting 50,000 light-years away on the far side of the Milky Way? For magnetars, that distance is not a safety guarantee. On December 27, 2004, satellites orbiting Earth saw this clearly. A magnetar called SGR 1806-20 unleashed a spike of gamma rays that hit our planet after crossing most of the galaxy. The pulse lasted about 0.2 seconds. In that tiny slice of time, the magnetar released as much energy as the sun emits in roughly 250,000 years. Detectors designed to handle bursts from distant galaxies went off scale. Some spacecraft instruments automatically shut down to protect themselves from the sudden flood of high-energy photons. That event is your reference point for what a giant flare means in Magnetar language. It is not a normal burst, not a small starquake. It is the extreme case where a large portion of the magnetosphere and crust snap into a new configuration at once. From Earth, all you see is a sharp spike in gamma rays, followed by a longer tail of X-ray emission. Inside that first fraction of a second, the power output is so large that the numbers almost look like misprints. To get a sense of scale, take the initial spike of that 2004 flare. It carried something like 10 to the power of 46 joules of energy. Just saying the number does not help much, so compare it with the most destructive devices humans have ever built. The largest nuclear bombs tested release on the order of 10 to the power of 17 joules each. To match the energy in that single spike, you would need around 10 to the power of 27 of those bombs. That's a billion megatons, all going off in less than a second, coming from a star only about 20 kilometers, 12 miles, across. The power it can release is on a scale that makes human weapons look irrelevant. You might think this was a one-time monster event, a unique outburst that we were simply unlucky enough to catch. The record says otherwise. We have seen only a few giant flares, but they show a pattern. In March 1979, an event from a source now known as SGR 0525-66 in the Large Magellanic Cloud lit up detectors. In August 1998, another flare came from SGR 1900+14, about 20,000 light-years away. Then the 2004 flare from SGR 1806-20 arrived. 3 events in different systems, all so bright that instruments designed to watch the entire cosmos were momentarily overwhelmed by a single, compact object in our local group of galaxies. Only 3 really clear giant flares in several decades tells you they are rare. Having 3 at all tells you they are a real repeating part of Magnetar behavior, not a one-off glitch. Each one lets us see not just the raw power, but the structure of what's happening after the initial blast. Once that first spike passes, the show is not over. Right after the spike, the Magnetar does something even stranger. The field lines that were twisted and snapped during the flare can trap a bubble of plasma just above the surface. That plasma is made of electrons and their antimatter partners, positrons. They're held in place by the ultra-strong field in what you can think of as a magnetic bottle, a closed region where charged particles are forced to follow looping field lines and cannot easily escape. This trapped fireball is incredibly hot and dense. As it cools and slowly leaks energy through the twisted magnetosphere, you see a tail of X-ray emission that fades over minutes. That tail is not smooth. It's chopped up at the spin period of the Magnetar. Each time the hot region, tied to the magnetic field, rotates into view, the X-ray brightness peaks, and when it rotates out of view, the brightness drops. By studying how that tail decays and how the pulse shape changes, astronomers can infer details about the geometry of the magnetic field and the size and location of the trapped plasma region. So, how much did the 2004 flare really affect us here on Earth if it was so far away? The distance was around 50,000 light-years, about 300 quadrillion kilometers. That's a huge buffer, yet the flare still had measurable effects. The sudden gamma-ray pulse ionized parts of the upper atmosphere, changing how radio waves bounced around the planet for a short time. Instruments that monitor Earth's ionosphere saw anomalies that lined up in time with the flare. That means giant flares aren't just impressive fireworks shows. They're energetic enough to disturb planetary environments across interstellar distances. Now, run a simple thought experiment with that. If a Magnetar giant flare at 50,000 light-years can tweak Earth's atmosphere, what if a similar event happened much closer? Calculations suggest that if a giant flare went off within roughly 10 light-years of Earth, still more than twice the distance to Proxima Centauri, the gamma-ray dose at the top of our atmosphere could be strong enough to seriously damage the ozone layer. The surface wouldn't be instantly blasted, but the long-term increase in harmful ultraviolet radiation from the sun leaking through a thinned ozone layer would be a real threat to life. This breaks a comfortable rule of thumb that distance always makes things safe at the scale of a galaxy. For most normal stars, being tens of light years away is enough to forget about them in terms of direct hazard. With magnetars, you have to treat them as potential biosphere-level risks out to surprisingly large ranges. The good news is that we don't know of any highly active magnetars that close to Earth right now. The bad news is that our census is incomplete, and the galaxy has had billions of years to produce and move these objects around. So, giant flares show you the high end of what magnetar magnetospheres can do when they fail catastrophically. They prove that a 20-kilometer object can briefly outshine almost everything else in the galaxy at gamma-ray energies, and still have power left to trap a fireball of plasma and slowly leak it away. The next step is to look at the same compact star in quieter states, when it's not tearing up its magnetosphere in a huge flare, but still evolving. To see that, you have to track its rotation, how its spin slows, and how that spin sometimes suddenly jumps or slips as the interior and crust fight for control. You're used to the idea that the more extreme something is, the faster it spins, but magnetars flip that expectation. For neutron stars, they're the slow ones. Typical radio pulsars spin dozens of times per second, some hundreds of times per second. Magnetars usually turn once every 2 to 12 seconds. For a 20-kilometer, 12-mile wide object, that's still insanely fast, but by neutron star standards, it's sluggish. That slow spin is not an accident. It tells you one key thing. Magnetars have already dumped a huge amount of rotational energy into their surroundings. When a magnetar is born, right after the core collapse, it can start off spinning many times per second. Over time, its intense magnetic field acts like a brake. The rotating magnetic field drags against the plasma around the star, launches particle winds, and sends out electromagnetic radiation. All of that drains rotational energy. The stronger the field, the stronger the braking. So when you see a magnetar rotating once every few seconds, you are not looking at a gentle spinner. You are looking at the burned-out remains of a much faster engine that has been slammed on by magnetic braking for thousands of years. The spin period is basically a record of how much energy the magnetic field has already taken. If the spin holds all that history, can you use it as a tool? Can you treat the rotation like a clock and watch what is happening inside? That is exactly what astronomers do. Every time a magnetar rotates, it sweeps its beam of X-rays or gamma rays across your line of sight, and you see a pulse. X-ray telescopes can measure the arrival times of those pulses to a precision of fractions of a millisecond. Over days, months, years, you stack up these timestamps and build a very precise rotation record. If the star were a perfect rigid ball slowly spinning down, the pulses would come in exactly on schedule, just drifting gradually as the star loses energy. But that is not what you see. Sometimes, without warning, the timing jumps. The pulses arrive a tiny bit earlier than expected, or the period suddenly changes by a tiny fraction, like 1 part in a million. That may sound small, but for a 1.4 solar mass object, it means a huge change in angular momentum. These sudden changes are called glitches. They are too sharp and too big to be explained by slow external braking. They are the signature of something inside the star rearranging itself and dumping angular momentum into the crust. The best explanation involves that superfluid interior you met before. Inside the crust, the neutron superfluid can rotate at a slightly different rate than the solid outer layer. It stores angular momentum in quantized vortex lines, microscopic whirlpools that carry rotation. Over time, those vortices can pin to the crust and then suddenly unpin, letting the superfluid transfer spin to the outer shell. When that happens, the crust speeds up just a little, and your pulse arrival times shift. From Earth, with a good X-ray timing instrument, you see a sharp step in the period or its rate of change, and you know the internal rotation profile has just changed. If glitches are internal, why do they sometimes show up right when the star is most active on the outside? What links the interior rearrangement to the bursts and flares you already saw? In several magnetars, glitches have been observed to coincide with X-ray outbursts. The spin changes right as the high-energy emission spikes. That means the superfluid core, the solid crust, and the magnetosphere are not acting separately. They are coupled. A starquake can shift the crust, which can change how the vortices are pinned, which can trigger a flow of angular momentum from the interior, while at the same time the crustal motion yanks on magnetic field lines and powers an outburst. You can think of it like this. The star's rotation, its surface fractures, and its magnetospheric flares all jerk in the same episode. One event, like a crust failure, can show up as a change in the spin period, a rearrangement of the magnetic field, and a spike in X-rays, all at once. That is why timing and radiative behavior together are so important. You're not just measuring a spin rate, you are watching a multi-layer, multi-component system release stress through different channels, all tied together by the same physics. So far, all of this fits the picture of magnetars as relatively young, high-field neutron stars, spinning every few seconds and gradually slowing down. But recent observations hint that this is only part of the population. There are candidates for ultra-long period magnetars, objects that take thousands of seconds, close to an hour, to complete one rotation. At those rates, their rotational energy is mostly gone. They are not bright because of spin down. They are still magnetically strong, but the engine they use to power activity is the decay of the magnetic field itself, not the loss of rotational energy. These ultra-slow rotators are hard to find. Their pulses are widely spaced, often weak, and easy to miss in surveys tuned to faster pulsars. If they are common, it means we've been looking at a biased sample, mostly catching the young, energetic magnetars and missing the older, slower, fainter majority. That would change the story you tell about magnetar lifetimes and about how long they can stay active. It would also mean that the line between magnetar and ordinary neutron star is not just about age, but about how the field and rotation have evolved along different paths. All of this destroys the simple mental image of a neutron star as a rigid, solid ball spinning down smoothly. Once you account for glitches, you are forced to acknowledge that the interior behaves like a quantum fluid, partially decoupled from the crust. Vortices pin and unpin. Superfluid regions spin at different rates. Magnetic braking tries to slow the outer layers. Crustal fractures and magnetospheric flares feed back into the spin. The neutron star becomes a layered object with complex internal dynamics, not a solid sphere. Magnetars push this complexity to the foreground. Their strong fields make magnetic braking intense. Their crusts are under more stress, so starquakes and glitches are more common. Their emission is bright enough that you can see the timing changes and the bursts clearly, even from thousands or tens of thousands of light years away. They are the neutron stars where this messy internal physics is impossible to ignore, because it literally shows up in the pulse timings and the sudden flares. So now you have a compact object that is not only magnetically extreme and prone to quakes and flares, but also internally unstable in a subtle quantum mechanical way. The next question is, what does all of that do to the star's surface, the thin layer that actually radiates most of the X-rays you see? And what kind of matter sits just under that skin when you push density and magnetic field strength even further? How hostile does a stellar surface have to get before you stop using words like hot gas and start calling it something closer to a controlled nuclear accident? A magnetar surface is in that regime. Its temperature sits at a few million Kelvin compared to the sun's surface at about 5,800 Kelvin. That's roughly a factor a few hundred hotter. At those temperatures, atoms can't stay together in any normal way. Electrons are stripped off, so instead of neutral atoms and molecules, you have bare nuclei and a sea of free electrons. The glow from this layer shows up mostly as thermal X-rays, not visible light. And that whole emission zone, the atmosphere, is only a few centimeters thick, maybe the thickness of your hand, spread over a sphere 20 kilometers, about 12 miles across. You don't have a deep, complicated atmosphere like Earth, or even like the Sun. You have a razor-thin plasma shell, extremely hot, pressed down by gravity that is billions of times stronger than what you feel on Earth. If the atmosphere is that thin and that violent, does the whole star at least behave like a smooth, uniform radiator, just one hot ball glowing steadily? Observations say no. When you look at magnetars in X-rays and model how the brightness changes as they rotate, you find that the surface is not uniform. There are hotspots, regions only a few kilometers across, where the temperature is significantly higher than the surroundings. For a 20-kilometer star, a hotspot a few kilometers wide is a big chunk of the surface. But in terms of area, it's more like a small country or a large city sitting on the face of the star. That patch can be radiating at higher temperature, sending out more X-rays, while the rest of the crust is still only at a few million Kelvin. Those hotspots aren't random. The ultra-strong magnetic field near the surface funnels heat and particles along specific field lines. Where those lines dive back into the crust, they can dump energy into a localized area and keep it hotter than the surroundings. During outbursts, new hotspots can appear, old ones can fade, and their locations can shift. By fitting how the X-ray brightness rises and falls during each spin, astronomers can reconstruct where the hot regions are, how big they are, and how they move over time. So even when the star is not in a giant flare, its surface is patchy, constantly rebalanced by the magnetic field. If the field can control where the heat comes out, does it also change how the light itself moves near the star? Near a magnetar, the answer is yes, down to the level of individual photons. The magnetic field close to the surface is so strong that it affects the vacuum around the star. According to quantum electrodynamics, empty space is never truly empty. It is filled with virtual particle pairs appearing and disappearing. In a field as strong as a magnetar's, those virtual particles line up with the field and give space itself different optical properties depending on the direction of polarization of the light. That effect is called vacuum birefringence. In plain terms, photons whose electric field is oriented one way see a different index of refraction than photons oriented another way. The result is that the region around the magnetar acts like a natural polarizing filter for X-rays. Light leaving the surface gets its polarization state rotated and sorted by the field it passes through. This is not just a curiosity. New X-ray polarimetry missions are starting to measure this polarization directly. If you detect the predicted polarization patterns, you are not only confirming the crazy magnetic field strength, you are testing quantum field theory in a regime that no laboratory magnet can reach. If the atmosphere and the near vacuum are already that modified, what does matter look like a bit deeper down, where the pressure and density ramp up even further? As you move below the crust toward densities around 10 to the power of 14 kilograms per cubic meter, theories predict that nuclear matter stops arranging itself as separate, roughly spherical nuclei. Instead, it organizes into extended structures that minimize energy under extreme compression. Protons and neutrons can form rod-like shapes, spaghetti, slab-like layers like lasagna, and more complex three-dimensional networks. This whole family of phases is called nuclear pasta. Nuclear pasta is not just a funny label. These shapes change how heat flows, how the crust breaks, and how the magnetic field threads the matter. Rods and slabs can channel currents differently than a uniform fluid or a simple crystal. They may make some directions easier for heat and magnetic flux to move than others. That, in turn, can influence how hotspots appear and disappear on the surface, how starquakes propagate, and how the magnetar cools over thousands of years. We cannot reproduce this material on Earth because you would need both the density of a neutron star and its gigantic magnetic field at the same time, over macroscopic volumes. The only place it exists, as far as we know, is inside neutron star crusts, especially in magnetars. So now stack all of this together. You have a surface layer at a few million Kelvin where atoms are stripped apart and the atmosphere is only centimeters thick. You have hotspots controlled by twisted magnetic fields that make the star's emission highly uneven. You have vacuum birefringence in the space above the surface, turning the surrounding region into a built-in X-ray polarizer. Beneath your feet, if you could stand there, the crust transitions into weird nuclear pasta phases that determine how the star responds to stress and how it moves heat around. None of this fits into a simple picture of a neutron ball with one clean equation of state and a smooth surface. That is why magnetar surface emission is so important. When you measure the spectrum of the X-rays, their polarization, their pulse shapes, and their changes over time, you are not just learning about a single object, you're probing physics in conditions that no accelerator, no fusion experiment, no magnet on Earth can reproduce. The atmosphere, the hotspots, and the layers just below them turn the magnetar into a laboratory for dense matter and extreme fields. And this is before you even compare them directly to normal neutron stars and pulsars, where the same basic skeleton behaves much more quietly. Once you put magnetars and ordinary neutron stars side by side, it becomes clear that these objects are not all copies of a simple model. They are a whole spectrum of states, with magnetars occupying the most violent end. How can two dead stars look almost identical on paper but behave like completely different objects? That is a situation with magnetars and normal neutron stars, the radial pulsar you hear about in most basic astronomy talks. Both types usually weigh around 1.4 times the mass of the Sun. Both are roughly 20 kilometers, about 12 miles, across. If you only measured mass and radius, you would say they share the same basic skeleton. The difference is in the magnetic field and the energy budget that runs the show. A typical radial pulsar has a magnetic field of about 10 to the power of 12 Gauss. That is already far beyond anything near Earth, but in neutron star terms, it's middle of the road. The main power source for that pulsar is rotational energy. It spins rapidly, sometimes many times per second, and as it spins down, it sends out radio waves and other radiation. The pulses you detect are basically the lighthouse beams from that rotating magnet. A magnetar with a field up to 10 to the power of 15 Gauss changes the priorities completely. Its field is so strong that the energy stored in the magnetism itself dominates. It still spins and spins down, but most of the X-rays and gamma rays you see are powered by the decay and rearrangement of the magnetic field, not by the loss of rotational energy. Same size, similar mass, totally different energy source. If the energy source is so different, you should expect the way they talk to us, their signals, to also be different. Standard pulsars are famous for their amazingly regular radio pulses. You can time them like atomic clocks. The pulses arrive at fixed intervals with only very slow drift as the star spins down. Magnetars don't behave like that. They can produce radio pulses, but they are usually irregular. Their main output is bursts of X-rays and gamma rays, plus big changes in their persistent X-ray brightness during outbursts. Instead of a steady, clock-like ticking, you get violent, unpredictable activity. Short bursts, long tails, giant flares. Timing is still important, but the pattern is much more chaotic. So at first glance, it looks like you have two clean categories: steady radial pulsars on one side, bursting magnetars on the other. But the more carefully you look, the less that separation holds. There are neutron stars with magnetic fields close to magnetar levels, but whose behavior looks more like high-field pulsars. They spin down like ordinary pulsars, they emit radio waves, but their field strength pushes into the range you used to reserve for magnetars. On the other side, there are objects classified as magnetars that have been seen producing radio pulses like regular pulsars, especially during and after outbursts. These crossover objects are important because they tell you the neutron star zoo is not split into two separate species. It's a continuous landscape. Magnetic field strength, spin period, age, and environment all blend to produce a range of behaviors. Magnetars are just the extreme corner of that space, where the field is so strong and the magnetic decay so important that bursts and flares dominate. High-field pulsars sit near that corner, sharing some traits. Ordinary pulsars lie further away, where fields are weaker and spin down is the main driver. There is no clean wall between them, just a smooth transition. If the categories are fuzzy, does that mean magnetars stay wild forever, or do they evolve into something more ordinary over time? The magnetic field has to decay. Over roughly 10,000 years, the ultra-strong field of a magnetar weakens. As that happens, the power available from magnetic decay drops, the outbursts become rarer and weaker, and the persistent X-ray luminosity falls. The star cools, its surface temperature drops, and its hotspots fade. Eventually, it may end up as a relatively quiet neutron star, emitting only weak X-rays from residual heat, or even slipping below our detection thresholds entirely. That decay timescale is tiny compared to the age of the Milky Way, which is more than 10 billion years. That is why we only see a small fraction of all the magnetars that have ever formed. Most of them have already gone through their active phase and turned into dim, hard-to-spot remnants. The young, noisy magnetars we detect are like the tip of an enormous iceberg. Below the surface, in terms of observational sensitivity, there's a huge hidden population of old, faded objects we don't see. Before magnetars entered the picture, it was tempting to treat neutron stars as one fairly uniform family. You tweak the magnetic field a bit up or down, you change the spin period, but you still think in terms of one basic behavior, a rigid ball spinning down. Magnetars kill that simple view. Once you push the magnetic field to 10 to the power of 14 or 10 to the power of 15 Gauss, you see entirely new observational classes. Bursts, giant flares, strong timing noise, huge glitches, strange X-ray spectra, polarization signals shaped by quantum effects in the vacuum. Magnetic field strength is no longer a detail. It is a primary parameter that changes almost everything. So now when you talk about neutron stars, you cannot just say, here is the mass, here is the radius, job done. You have to ask, how strong is the field, how is it structured, how fast is it decaying, and how is that field coupling to the crust and the interior? Those questions decide whether the object looks like a quiet radio pulsar, a flickering X-ray source, a bursting magnetar, or something in between. And once you accept that, the next leap is to ask where magnetars fit into other cosmic mysteries that also involve sudden, intense bursts of energy, like fast radio bursts that briefly outshine whole galaxies in radio waves. That connection is where magnetars stop being just weird neutron stars and start shaping how you map the universe itself. How do you get a radio flash that for a thousandth of a second is brighter than an entire galaxy, then vanishes as if nothing happened? That is what fast radio bursts, FRBs, are doing. Each one is a very short blip of radio waves, lasting a few milliseconds or less, coming from far outside our galaxy. In that tiny slice of time, they can put out as much energy in radio as the sun emits in days. Some sources fire once and go quiet, at least as far as we can tell. Others repeat, sometimes with complicated patterns, sometimes almost randomly. For years, nobody had a solid answer to a simple question. What engine can switch on that fast, dump that much energy into radio, and then shut off again without blowing itself apart? So what kind of object can produce that kind of burst on demand, over and over, and survive? The first strong clue came not from some distant galaxy, but from inside the Milky Way. In 2020, a magnetar called SGR 1935 plus 2154 suddenly spat out a radio burst so bright that if you moved it to another galaxy, it would have looked exactly like an FRB. At the same time, X-ray and gamma-ray detectors saw high-energy activity from the same source. This was the first time we caught a magnetar in the act of doing something that, at cosmological distances, would be labeled a fast radio burst. That single event tied at least some FRBs directly to magnetar activity, to starquakes and magnetic reconnection flares in ultra-strong fields. The picture is straightforward, but extreme. A starquake or magnetic twist near the surface of the magnetar suddenly reshapes part of the magnetosphere. Field lines reconnect, particles get slammed to ultra-high energies, and a very short, very focused radio flash is produced, along with X-rays or gamma rays. The magnetar does not explode or tear itself apart, it just rearranges a tiny fraction of its magnetic structure and vents energy. That is enough to produce a millisecond pulse that would stand out, even if the source were hundreds of millions of light years away. If one magnetar in our own galaxy can behave like a fast radio burst engine once, are there systems out there that are basically built to do this repeatedly, with the environment constantly changing and pumping the engine? Recent observations say yes. Some repeating FRBs have patterns that point strongly to magnetars in binary systems, where the magnetar orbits a more normal star. China's FAST telescope, a 500-meter radio dish, has followed some of these repeaters for months and years. In certain cases, the burst rate seems to rise and fall in sync with the likely orbital period. As the Magnetar moves closer or farther from its companion, it plows through different parts of the companion's stellar wind or magnetosphere, changing the local plasma density and magnetic structure. That changing environment can modulate how easily the Magnetar's energy can escape as radio bursts, and where in the magnetosphere the bursts are produced. In some orbital phases, the conditions are right, the magnetosphere is loaded, and bursts are frequent. In others, the system is quieter. By tracking these patterns, you start to see not just a random storm of bursts, but a system where orbital motion, stellar winds, and magnetar activity are all linked. The burst train becomes a way to map the binary system itself. If the engine is a magnetar sitting in a messy, magnetized environment, the radio signal itself should carry fingerprints of that chaos. That is exactly what you see. FRB signals arrive at Earth with extreme polarization, meaning their electric fields are strongly aligned in particular directions. They also show large Faraday rotation, where the plane of polarization is twisted as the waves pass through magnetized plasma, and they show scattering that smears the pulses in time. All of that tells you the radio waves have crossed regions with strong magnetic fields and dense, uneven plasma, not clean, empty space. Models where the bursts are generated within a few stellar radii of a magnetar, inside its magnetosphere, or just outside it, match these signatures well, especially for repeaters embedded in dense, magnetized regions, like star-forming zones or near the centers of galaxies. In that scenario, the radio waves start life in an environment dominated by the magnetar's own field, then pass through the messy plasma around it, then through the host galaxy, then the thin gas between galaxies, and finally through the Milky Way before reaching our antennas. Each layer leaves its mark on the signal, in the form of dispersion, polarization changes, and scattering tails. And if every burst carries a record of the material it has crossed, what can you do with thousands of them scattered across the sky? This is where magnetars stop being just cosmic hazards and turn into tools. As a radio pulse travels, lower frequency waves get delayed more than higher frequency ones by the free electrons along the path. The amount of delay tells you how many electrons the pulse has passed through, summed over the whole journey. That quantity is called the dispersion measure. For an FRB at a known distance, that dispersion measure gives you an estimate of how much ordinary matter, normal protons and electrons, lies between us and the source. When you collect FRBs from many directions at many distances and tie at least some of them to magnetars in distant galaxies, you can start to build a map of the missing baryonic matter in the universe, the ordinary matter that we know must exist from cosmology, but that does not show up in stars or bright gas. A lot of it is spread out in thin filaments between galaxies, too diffuse to see directly. FRBs use that diffuse gas as a medium, and each burst is a probe shot through a different part of the cosmic web. By measuring their dispersion measures and comparing them with models of where galaxies and clusters are, astronomers can literally weigh the intergalactic medium. So the same type of object that can, in principle, damage a planet's atmosphere with a giant flare is also helping us count the atoms between galaxies. Magnetars, through FRBs, are turning into tools for precision cosmology, not just weird neutron stars. And that brings you back closer to home, because if these engines are scattered across the universe, driving FRBs and lighting up distant galaxies, there must be a set of them in our own Milky Way that we can study in far more detail. The next step is to look at those neighborhood monsters one by one, the specific magnetars whose flares and bursts have already slammed our detectors and rewritten our theories. You have seen what magnetars can do to detectors and to theory, so the next question is simple and unsettling. Which specific objects in our neighborhood have already gone off? The story starts in 1979 with an event that did not fit into any box astronomers had at the time. On March 5th of that year, satellites picked up a blast of gamma rays from a source in the Large Magellanic Cloud, a small satellite galaxy about 160,000 light-years away. The source is now called SGR 0525-66. The flare was so intense and so short that when people tried to explain it with a normal neutron star model, the numbers fell apart. To get the observed behavior, you needed magnetic fields around 10 to the power of 14 to 10 to the power of 15 Gauss, several orders of magnitude above standard pulsars. That one event forced people to seriously propose a new kind of neutron star, one where the magnetic field itself dominates everything, the magnetar. If that first flare in 1979 was a warning sign, the next big one in 1998 was a stress test. On August 27, 1998, a source about 20,000 light-years away, called SGR 1900+14, produced a flare that saturated multiple satellites. Instruments designed to handle bursts from across the universe hit their limits from something inside our own galaxy. But the really important part was not just the initial spike. The afterglow, the X-ray tail that followed, carried a lot of structure. It faded over minutes, and it showed clear periodic modulation at the spin period of the neutron star. On top of that, careful analysis found quasi-periodic oscillations, those seismic tones you heard about earlier. That combination, a huge spike, then a modulated tail, then oscillations, looks exactly like you expect if a starquake fractures the crust, the magnetosphere gets rearranged, and a trapped fireball of electron-positron plasma hangs just above the surface in a magnetic bottle. SGR 1900+14 became a testbed. The data were rich enough that theorists could tweak starquake models, trapped fireball models, and magnetospheric reconnection scenarios against real numbers. And the fits pointed consistently to the Magnetar interpretation, not to any simpler normal neutron star flare. You might wonder if there's a clear high point, a single event that shows you the upper limit of what these objects can do. That role is still held by SGR 1800-20. On December 27, 2004, it fired the giant flare you heard about earlier from around 50,000 light-years away on the far side of the Milky Way. For a brief moment, at gamma-ray energies, it was the brightest non-solar object in our sky by a huge margin. The energy in the first 0.2 seconds, about 10 to the power of 46 joules, made it the record holder for Magnetar flares. If that same event had happened 10 times closer, around 5,000 light-years away, the gamma-ray dose at Earth would have been much higher, and the impact on our atmosphere could have been severe. SGR 1806-20 is often used as the reference monster, the extreme case that sets the scale for hazard calculations. It shows that a compact object only about 20 kilometers across, with the right magnetic configuration, can release enough energy in less than a second to outshine almost everything else in the galaxy at high energies. And it did that without destroying itself. The Magnetar is still there, still rotating, still emitting. The crust and magnetosphere were rearranged, not obliterated. At this point, you might ask, how many of these things do we actually know about, and where are they sitting? As of the early 2020s, astronomers had confirmed on the order of 24 magnetars in and around the Milky Way, plus a number of strong candidates. They do not all live in the same kind of neighborhood. Some sit in active star-forming regions where massive stars are being born and dying all the time. Others are found near supernova remnants, the expanding shells of gas left behind after the explosion that created them. A few are close to dense star clusters where interactions and even stellar mergers are more common. That spread in environment is a clue. It hints that there may be multiple formation channels. Some magnetars probably come from single massive stars in the 10 to 25 solar mass range, dying in core collapse supernovae with strong rotation and dynamos, the story you already heard. Others might be born in binary systems, where mass transfer or mergers spin up the core before collapse. There are also ideas where neutron star mergers briefly create hypermassive magnetars before they collapse into black holes. The census of known magnetars is still small, but their locations point to a variety of paths that can all land at the same kind of object, a compact star with a magnetic field dialed to maximum. So if there are only a few dozen known, does that mean there are only a few dozen in the whole galaxy? The answer is no, and this is where the tension ramps up again. When you combine supernova rates, magnetic field decay models, and the active lifetime of a magnetar, you get a very different number. Magnetars probably stay bright and obviously magnetar-like for around 10,000 years. The Milky Way has been forming massive stars for billions of years. With even a modest fraction of core collapsed supernovae producing magnetars, you quickly expect there to have been millions of magnetars formed over the galaxy's history. Most of those are no longer active in X-rays or gamma rays. Their fields have decayed, their surfaces have cooled, and they no longer stand out from the background. They're still there as compact remnants, still with strong gravity, still with non-zero magnetic fields, just not bright enough for our current instruments to pick out, unless we are very lucky. That means the night sky is not just dotted with visible stars and a few known neutron stars. It is filled with a hidden population of dead magnetic monsters spread through the disk and halo of the Milky Way. You live inside a galaxy where the dangerous active magnetars you can see are just the loudest ones in a much larger crowd. Most of their older relatives are dark, undetected, and effectively invisible to you. That is uncomfortable, but it also means the ones you do see are valuable because they are the rare cases where the magnetic field is still strong enough to light up the extreme physics. And that brings you to a key point: how we actually see them at all. Because without the right X-ray and gamma-ray instruments, these objects would have stayed hidden, and the whole concept of magnetars would have been delayed by decades. How do you even notice a city-sized star that only screams in X-rays and gamma rays when your eyes are blind to that part of the spectrum? The only way you ever met magnetars at all is because we built machines specifically to catch violent high-energy events, and those machines started seeing signals that normal neutron stars could not explain. The first wave of detectors, like the Vela satellites, CONUS, and later missions such as RxTE, SWIFT, and Fermi, were not built for magnetars. They were built to look for nuclear tests or to study gamma-ray bursts from distant galaxies. They stare at huge chunks of the sky, all the time, watching for sudden spikes in X-rays and gamma rays when something anywhere in their field of view suddenly gets thousands or millions times brighter in high-energy light. They trigger, record the burst, and try to figure out where it came from. That is exactly how the first soft gamma repeaters, the early magnetar candidates, showed up as sources that suddenly flared again and again in high-energy bands where ordinary stars are basically dark. Once a satellite like SWIFT or Fermi sees a spike, the next question is, where on the sky did that come from? Can you aim more precise instruments? These explosion hunters can usually localize a burst to a region small enough that X-ray and optical telescopes on other satellites or on the ground can follow up. That handoff is critical. The wide field instruments catch the flare and send an alert, and then narrower field, sharper eyes zoom in to study the source in detail. Without this chain, magnetars would just be anonymous flashes with no known host. After that first detection and localization, the job shifts from "there was a flare" to "what kind of object is this and how does it behave over time?" This is where observatories like Chandra, XMM Newton, and NICER come in. They can point very precisely, collect X-rays over long exposures, and measure both timing and spectra. Timing means they record the arrival time of each photon, so you can reconstruct pulse periods and see how they change. Spectra mean you can see how the brightness is distributed over different X-ray energies, which tells you about temperature and emission mechanisms. On top of that, a change in pulse arrival times of just a few milliseconds out of a period of a few seconds can reveal a glitch, a sudden rearrangement in the crust or superfluid interior. So a magnetar you can't touch still tells you about its internal physics just through its timing and spectra. High-energy satellites do not work alone. Whenever a magnetar is active, or when it behaves like a fast radio burst engine, radio telescopes join the chase. Big dishes and arrays from places like Arecibo in the past to FAST and the VLA listen for radio pulses and bursts. If a magnetar turns on in radio, you suddenly gain another channel to time its rotation and study its emission geometry. At the same time, infrared and optical telescopes search the same patch of sky for counterparts, for faint stars or clusters at the magnetar's position. Sometimes you find that the magnetar sits in a young star cluster, confirming it is a recent product of massive star evolution. Sometimes you see a supernova remnant shell around it, the debris of the explosion that created it. Each wavelength band fills in a different part of the story: environment, age, possible binary companions, and the broader context of the Magnetar's birth. So far, all of this is using standard tools in X-rays, gamma rays, radio, optical, and infrared. The next step is more aggressive, directly testing how light behaves in the extreme fields near a magnetar, and even listening for the star's vibrations and gravitational waves. Next-generation X-ray polarimeters are being built and launched with exactly this in mind. They do not just count how many X-ray photons arrive at what energies and times. They measure the polarization, the orientation of the electric field of each photon. As you heard earlier, near a magnetar, the vacuum itself is expected to act like a polarizing medium because of quantum electrodynamics effects. If those predictions are right, the X-rays from the surface should carry a very specific polarization pattern, depending on the magnetic field geometry and the viewing angle. Measuring that pattern is a direct test of our best quantum theory in a regime no lab can reach. In parallel, gravitational wave observatories like LIGO, Virgo, and Cagra are watching for tiny ripples in spacetime. Their main targets are mergers of black holes and neutron stars, but magnetars are on their list too. A giant flare or a major starquake should shake the star's mass distribution, producing a burst of gravitational waves, although much weaker than a full merger. If detectors ever see a gravitational wave chirp or ring down at the same time as a magnetar flare in gamma rays, that would open a completely new window into the interior, letting you probe the equation of state and the crust-core coupling with spacetime, not just with light. When you put all of this together, you see why magnetars crush a common excuse in physics: the idea that some regimes are too extreme to ever be tested in nature. Here, you have objects that naturally reach densities beyond nuclear, magnetic fields stronger than anything you can make on Earth, and temperatures of millions of Kelvin, all in one place. They are not thought experiments, they are real, scattered around your galaxy and beyond. And our instruments, from wide-field gamma-ray monitors to narrow-beam X-ray telescopes, sensitive radio arrays, polarimeters, and gravitational wave detectors, are finally good enough to read what these stars are writing into the sky. That means every new magnetar's flare, every timing glitch, every polarization measurement is not just more data on some weird neutron star. It is a test of how far our theories of matter, fields, and spacetime can be pushed before they break. And magnetars are not done pushing. The closer you look at their fields and their light, the more you are forced to bring in full quantum field theory, even to describe what empty space is doing. That is where the story goes next, into the quantum weirdness around magnetars, where the vacuum itself stops behaving like nothing at all. How can something you call empty space start acting like a material with its own optical rules? Around the magnetar, that's exactly what happens. At the field strengths you're dealing with here, quantum electrodynamics says the vacuum is not just nothing, it's a busy background where virtual particles flicker in and out of existence so fast you normally never notice them. A magnetar's magnetic field, up around 10 to the power of 11 Tesla, forces those virtual electron-positron pairs to line up and respond. The result is that empty space gets an index of refraction, the same kind of property glass or water has, and that index now depends on how the light is polarized relative to the magnetic field. So light with its electric field vibrating parallel to the magnetic field travels slightly differently from light vibrating perpendicular to it. One polarization mode experiences a slightly higher optical density than the other. Over large distances near the star, this difference builds up. A beam of X-rays leaving the surface gets split into components that have their polarization rotated and filtered by the vacuum itself. This effect is called vacuum birefringence. It's not a poetic name, it just means the vacuum behaves like a birefringent crystal, something that has two different refractive indices depending on polarization. That's already a huge step away from everyday physics, because you're used to treating empty space as a perfectly neutral background, not as a medium with its own optical properties. If the vacuum can bend and separate polarizations, what does a field this strong do to individual photons with very high energy, the kind of X-rays and gamma rays magnetars spew out? In normal, weak field environments, high-energy photons travel in straight lines unless they hit matter. Their identities are stable. They don't just split into lower-energy photons or merge with other photons for no reason. But in a magnetar's field, the rules change. When the magnetic field is above about 10 to the power of 10 Tesla, quantum electrodynamics allows processes that are basically shut off elsewhere. One key process is photon splitting. A single high-energy X-ray photon can convert into two lower-energy photons, even in the absence of matter, as long as energy and momentum are conserved and the polarization conditions are right. The magnetic field essentially acts like a catalyst, providing the background needed to make the reaction possible. The reverse can also happen. Two photons can merge into one with higher energy. These channels are either forbidden or incredibly rare in weak fields, that you can ignore them in normal astrophysics. Near a magnetar, they become efficient enough to matter. They can reshape the spectrum of escaping radiation, cutting off the highest energies and redistributing that energy into more numerous lower energy photons before the light ever leaves the magnetosphere. So now, the light you detect from a magnetar has already been processed twice, once by the vacuum's birefringence and once by photon splitting and merging in the strong field. That raises a sharp question. Are we just taking QED's word for this, or can we actually test these predictions in the real universe? This is where X-ray polarization measurements become powerful. If you can measure not just how many X-ray photons arrive and at what energies, but also how their polarization is oriented, you can compare those patterns directly to the detailed predictions of strong field quantum electrodynamics. Current and upcoming missions are doing exactly that. They look at magnetars during both quiet and active phases, and they record how the polarization fraction and angle change with energy and with the star's rotation. If the vacuum around the magnetar behaves as QED says, you get a specific set of signatures, like high polarization fractions in certain energy bands, and characteristic swings in polarization angle as the hotspots and magnetic poles rotate into and out of view. If the data line up, that is a very strong confirmation that QED holds even in fields that make every laboratory magnet look trivial. If the data deviate, if you see polarization behavior that cannot be matched by any QED-based model, that would be a serious hint of new physics beyond the standard model, right there on the surface of a neutron star. In that sense, a magnetar becomes a particle physics experiment with a diameter of 20 kilometers. Instead of building a collider that reaches insane field strengths over a few meters, the universe gives you a compact star where those conditions exist naturally and persistently. Your job is to read the light coming off it with enough precision to see the quantum effects. This is a complete break from how you usually think about magnetism. In lab magnets or in planetary fields, classical electromagnetism is more than enough. You can treat the field as smooth lines in space, and you do not need to worry about virtual particles or vacuum polarization. In a magnetar, that classical picture is not wrong, but it is incomplete. The field is so strong that the quantum structure of the vacuum cannot be ignored. You are forced to use the full framework of quantum field theory just to describe how light travels, how it splits, and how it emerges from a small region above the surface. The fact that you can observe any of this from tens of thousands of light years away is one of the strangest aspects of magnetar science. You are not putting sensors near the star. You are not running experiments under controlled lab conditions. You are catching a tiny fraction of the photons that manage to escape a system like this. And yet, with timing data, spectra, and polarization, you can see the fingerprints of strong field QED on those photons. That means magnetars are not just wild neutron stars with big magnetic fields. They're working demonstrations that some of the most abstract parts of modern physics are not just math, they're active in nature, all the time in real objects. So you now have a star where gravity curves spacetime strongly, where matter is at nuclear density, where magneticism forces the vacuum itself to act like a material, and where light is constantly being reshaped by quantum processes before it escapes. The next step is to push the connection even further into the regime where magnetars overlap with gravitational waves and neutron star mergers, and where their extreme magnetism might help power some of the brightest explosions in the universe. How far can you push a neutron star before it stops being a star and turns into a black hole? And what happens in that narrow window where it is still hanging on? You see that at the end of a neutron star merger. When two neutron stars spiral together and collide, they do not always produce a black hole instantly. In many models, and probably in some real events, the first product is a hypermassive neutron star, held up for a short time by rapid rotation and intense magnetic fields. In that brief phase, the remnant is essentially a gigantic, ultra-hot magnetar with a mass maybe 2.5 to 3 times the Sun, spinning extremely fast and threaded by fields that have been amplified by turbulence and shear during the merger. That post-merger magnetar is not quiet. It is surrounded by debris, neutron-rich material thrown out during the collision at a significant fraction of the speed of light, tens of thousands of kilometers per second. The remnant's rotation and magnetic field can pump energy into that debris. Strong magnetic winds, Poynting flux, and particle outflows deposit power into the expanding matter. If the remnant survives for milliseconds, it adds some energy. If it survives for seconds or longer before collapsing to a black hole, it can inject a lot more. The timescale over which that magnetar-like object lives directly changes what you see from Earth. So how do you know if that is really happening and not just a nice model? You look at the light from the kilanova, the optical and infrared transient that follows a neutron star merger. In a simple radioactive decay picture, the brightness and color evolution are set by freshly made heavy elements decaying and heating the ejecta from within. The light curve fades in a predictable way as the energy from those decays drops and as the ejecta expands and cools. But in some observed kilanovae, the brightness stays high for longer than expected, or the color evolution does not match a pure radioactive model. If you add a magnetar remnant injecting rotational energy into the ejecta, the picture changes. The extra power boosts the luminosity and can keep the ejecta hotter for a longer time. That can make the kilanova brighter in the optical and shift the peak, or extend a blue component that would otherwise fade quickly. The timescale of the light curve, how fast it brightens and dims, becomes a clue to how long the post-merger remnant stayed as a neutron star before collapsing to a black hole. In that sense, the kilanova is not just telling you that heavy elements were formed, it's telling you how strong the remnant's magnetic engine was and how long that magnetar phase lasted. If neutron star mergers can give you these ultra-heavy, short-lived magnetars, can isolated magnetars also talk to you through space-time itself, not just light? Every time a magnetar has a starquake, its mass distribution changes, the crust cracks, parts of the star shift slightly, and the shape of the star, at least in small ways, is altered. In general relativity, anytime a massive object changes its quadrupole moment, it should emit gravitational waves, ripples in spacetime that travel out at the speed of light. For magnetar quakes, those waves are expected to be weak compared to full mergers, but they should be there. Detectors like LIGO, Virgo, and CAGRA are already listening for them. When a giant flare goes off in gamma rays, those instruments can check their data around the same time window for any coincident signal at frequencies expected for crust and core oscillations, maybe hundreds to thousands of hertz. So far, we do not have a clear detection of gravitational waves from a magnetar flare, only upper limits. But even those limits are useful. They tell you how much the star's shape could have changed and how strongly the crust and core are coupled. A future detection, even a marginal one, would be a direct probe of the star's interior using space-time vibrations, not just photons. You might ask whether the oscillations you already see in X-rays after giant flares are telling part of the same story. After large magnetar flares, the X-ray tail sometimes shows quasi-periodic oscillations, QPOs, at certain frequencies. Those frequencies are thought to come from torsional modes in the crust and from coupled crust core modes, twisted motions that ring down over time. The exact values depend on the thickness of the crust, its composition, and how strongly it is tied to the core by the magnetic field and by nuclear pasta layers. So every QPO you measure is already a constraint on the internal structure. If you could combine that with gravitational wave data from the same event, you would suddenly have two independent views into the same oscillation. The X-ray QPOs give you the electromagnetic response, how the emission pattern modulates as the star vibrates. The gravitational waves would give you the direct mass motion, how the bulk of the star's matter is moving. Matching both against models of neutron star structure would let you pin down the equation of state, the relationship between pressure and density in matter far beyond nuclear density. Right now, that equation of state is one of the biggest unknowns in dense matter physics. Magnetars, through their quakes, flares, and potential gravitational wave signatures, turn into tools for narrowing down which equations work and which do not. So in neutron star mergers, magnetar-like remnants may control how bright and how long kilanovae shine. In isolated magnetars, starquakes might send out gravitational waves you could one day detect alongside X-ray flares. In both cases, the same basic physics, extreme magnetism and dense matter, shows up across different channels, light and gravity. That convergence raises one more question. If magnetars can change how mergers look and how stars vibrate, could they also be changing how the universe builds its heaviest elements, including the gold and uranium on Earth? How do you get from simple elements like hydrogen and helium to gold in your jewelry or uranium in a reactor, when normal stars cannot do that job? Heavy elements like gold, platinum, and uranium need what is called the rapid neutron capture process, the R process. That means you need a place with an insane density of free neutrons, where atomic nuclei get slammed with neutrons so fast that they don't have time to decay in between captures. For a long time, core collapse supernovae were the main suspect. Then, neutron star mergers moved to the front of the line, because their ejecta are incredibly neutron-rich. Magnetars don't replace those ideas, but they add extra, uncomfortable options you can't ignore. Start with the explosion itself. In a standard core collapse supernova, the hot proto-neutron star and neutrino flux set the conditions for the outflow, how dense it is, how hot it is, and how many neutrons are available. If the newborn remnant is a millisecond magnetar, spinning in thousandths of a second with a magnetic field around 10 to the power of 15 Gauss, that picture changes. The magnetar is not just passively sitting there, it's dumping rotational energy and angular momentum into the ejecta through its magnetic field. That extra energy injection can do several things at once. It can drive stronger winds from the surface, it can push the ejecta to higher speeds, and it can change how quickly the material expands and cools. All of that affects the density and temperature history of the outflow, and that history controls how easy it is to build heavy nuclei through rapid neutron capture. Compared to a standard supernova without a strong central engine, a magnetar-driven supernova might hold on to high neutron densities for longer, or process material in different layers at different rates. In simple terms, the magnetar can turn a normal explosion into a more powerful, more structured R-process factory. Then you have the winds that come directly off the magnetar itself. Along open magnetic field lines, especially near the magnetic poles, the magnetar can launch outflows of particles, magnetar winds. Now, these are not gentle breezes. They can carry neutron-rich matter away from the surface at a significant fraction of the speed of light. In numbers, that can be more than 0.1 times the speed of light, over 30,000 kilometers per second, roughly 19,000 miles per second. That combination of high speed, high density, and strong neutron richness is exactly the kind of environment where rapid neutron capture can run wild, building up heavy nuclei before the material expands and thins out. The key is the timing. The wind has to stay dense long enough for nuclei to grab neutrons faster than they can decay back to stability. The magnetic field helps by channeling the flow and possibly keeping it clumped for a while. As the wind expands into space, the nuclei formed there freeze out, locking in a distribution of heavy elements that depends on the detailed conditions near the magnetar surface. In principle, different magnetar birth events could leave different chemical fingerprints in the surrounding gas, depending on how strong the field was, how fast it spun, and how long it survived. So where does this leave you in the bigger picture? Does most of the gold and platinum in the universe come from magnetars, or are they just a side branch? Right now, that is still an open question. Neutron-star mergers clearly produce R-process elements, and we have seen the signatures in kilanovae. Some classes of supernovae also look like they contribute. Magnetar-driven explosions and magnetar winds sit in the mix as additional channels. Their total contribution to the cosmic inventory of heavy elements is still being debated, because it depends on how often millisecond magnetars are born, how strong their fields are, and how their outflows evolve. What is not in doubt is the main point. Once you add extreme magnetism and rapid rotation, the story of where heavy elements come from gets more complicated. Your gold ring may trace back to a neutron-star merger, to a rare kind of supernova, or to a magnetar-powered event that changed the outflow in just the right way to let our process nucleosynthesis run efficiently. You are wearing the output of extreme astrophysics on your finger, and magnetars may have been part of that chain. So by now, magnetars are involved in almost every edge case in high-energy astrophysics, from giant flares that can shake Earth's atmosphere, to fast radio bursts you use to map the intergalactic medium, to kilanovae, and maybe even to the origin of some of the heaviest elements. That raises one last, bigger issue. What do these objects do to our idea of how physics itself is organized? If one class of dead star can touch gravity, nuclear physics, plasma physics, quantum electrodynamics, and cosmology all at once, maybe the rules you thought were separate are not so separate after all. So what exactly do magnetars do to our idea of normal physics? Why do they feel so different from everything else you have heard about in space? The short answer is, they live in a parameter space that humans never evolved to understand. For you, safe numbers are things like room temperature, Earth gravity, a magnetic field you barely notice. For magnetars, the default settings are magnetic fields around 10 to the power of 11 Tesla, densities beyond what you get inside an atomic nucleus, and surface temperatures of a few million Kelvin. Those values are not special cases on the edge. They are the baseline conditions inside these stars. When you work in those ranges, your everyday intuition breaks. Concepts like solid, gas, vacuum, and magnetic field shift into new regimes. A solid crust is a kilometer-thick slab of nuclear material. A gas is a few centimeters of plasma at millions of degrees. Vacuum behaves like glass, changing how light moves. A magnetic field has enough energy density that you can talk about its mass. Magnetars force you to acknowledge that most of physics lives far away from human scales, and that the familiar world is just a very small, very mild corner of the full map. So what do you even call the field that studies an object like this? Are you doing astronomy, or nuclear physics, or plasma physics, or quantum field theory? The honest answer is, all of them at once. In a magnetar, gravity is strong enough to curve space-time on kilometer scales. Nuclear physics sets how the core and crust respond to pressure. Plasma physics controls the magnetosphere, the charged particles streaming along field lines. Quantum electrodynamics steps in to say how the vacuum itself changes in ultra-strong fields, and how photons split or change polarization. You cannot cleanly separate these pieces. A starquake, for example, is triggered by magnetic stress in the crust, but the way the crust breaks depends on nuclear interactions and on the structure of nuclear pasta. The flare that follows is shaped by magnetospheric plasma processes. The polarization of the resulting X-rays carries a signature of strong field quantum effects in the vacuum. The tiny change in the star's shape sends out a gravitational wave signal, which you would interpret using general relativity. One event, one star, forcing 4 or 5 separate areas of physics to talk to each other, whether you like it or not. What makes this more striking is that nobody ordered these conditions on purpose. Magnetars weren't designed as experiments. They're just a natural endpoint of certain massive stars collapsing with the right spin and field. The universe built them because the equations said they could exist, then left them scattered around galaxies as side effects of stellar evolution. For you, they are extremely inconvenient because they sit exactly in the regime where your theories are hardest to test on Earth. Every time you see a fast radio burst that lines up with a magnetar, you are being asked whether your models of coherent radio emission in strong fields actually work. Every time a giant flare slams your satellites and shows quasi-periodic oscillations, you are being asked whether your models of crust breaking and core coupling are correct. Every time you measure X-ray polarization that matches or disagrees with strong field QED predictions, the universe is effectively saying, "Here, this is your math in the wild. Are you sure you trust it?" The stakes keep climbing as you join these pieces together. If a large fraction of FRBs come from magnetars, then these stars are not just local curiosities. They are tools for mapping the missing ordinary matter between galaxies, using dispersion as a probe. If starquakes in magnetars produce detectable gravitational waves, they become direct probes of the neutron star interior, giving you a shot at the true equation of state of ultra-dense matter. If their surface emission really shows the vacuum birefringence and photon splitting that QED predicts, then magnetars become the only real-world laboratories where you can test quantum fields in magnetic fields far beyond anything you can generate on Earth. At that point, magnetars stop being exotic weirdos on the edge of astrophysics and start becoming central players in how you understand the universe. They help set the rules for dense matter, for strong field magnetism, for high-energy radiation processes, for where heavy elements come from, and for how you can use bright, short bursts to weigh the cosmic web. A single class of objects, small in number but extreme in behavior, ends up touching problems from the inside of an atomic nucleus to the structure of the universe on gigaparsec scales. So when you hear the words neutron star, it is easy to think dead star, end state, story over. Magnetars answer that with no. This is where the story gets weird. They are not the quiet gravestones of stellar evolution. They are the phase where the universe takes all the knobs you know about, gravity, density, magnetism, temperature, quantum physics, and turns them past the markings. They show you that the rules you learned from everyday physics were never the full set. They were just the training wheels version. Your real universe includes objects where empty space bends light, where magnetism has weight, where matter is squeezed into shapes we cannot make in any lab, and where a city-sized star can threaten planets tens of light years away. Magnetars do not just break the rules, they expose the real ones, the ones that only show up when the numbers are pushed to the absolute limit. And the more closely you watch them, the more they force you to admit that the universe is not just stranger than you thought, it's running on a level of physics you are only just starting to read. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.